Hi class, we continue our study in chapter 6 talking about quadrilaterals by moving into section 6.2. Section 6.2 we're talking about something called parallelograms, and these are very specific polynomials. So the two objectives in this section is we want to use relationships among sides and angles of these parallelograms, and I'll define what that is in a second. And then we want to use relations among consecutive angles and diagonals of different parallelograms. All right, let's start with the definition of what a parallelogram is. So a parallelogram is a quadrilateral, right, so that's four sides, with both pairs of opposite sides being parallel. So this side here is parallel with this side, and this side, the opposite side over here, is parallel with it as well. So parallelograms have special properties regarding their sides, angles, and diagonals, and we're going to talk a lot about those properties. But just remember, opposite sides are parallel. So in a parallelogram and all other convex quadrilaterals, right, we learned what convex means. It means there's no interior point to them. Opposite sides, all right, do not share a vertex, and opposite sides do not share a side. So AB here and CD are opposite sides, and CD, or AB and CD here, I mean BC and AD are opposite sides. Angle A is the opposite angle with angle C, and angle B is the opposite angle with angle D. All right, so we have opposite sides and then opposite angles. So here's a theorem, all right? This is the opposite sides of parallelogram. So if a quadrilateral is a parallelogram, then the opposite sides are congruent. So if ABC is a parallelogram, that's the notation for a parallelogram, then it must be, always, if it's a parallelogram, that side AB is congruent to side CD, and side BC is congruent to side DA, or AD, it doesn't matter how you say it. So opposite sides of parallelograms are congruent. Another one, opposite angles here. So if a quadrilateral is a parallelogram, then the opposite angles are congruent. So if ABC is a parallelogram, then these opposite angles, so angle C and angle A here are congruent or equal angles, and angle B and angle D here are congruent or are equal angles. All right, so let's do a proof, a two-column proof here. So let's use the given figure for a proof of theorem 6.2-1. So I want to prove here that the opposite sides are congruent. So given that figure ABCD is a parallelogram, that's all you're given, prove that side AB is congruent to side CD and BC is congruent to DA. All right, well, what you're going to have to do here is I put a diagonal in here, right? And I labeled some angles. We're going to notice that there's two shapes here are triangles. So we're going to use some type of something with triangles here. All right, so we're going to start a two-column proof to do this. All right, this is on the next slide right here. All right, so start with what's given. ABCD is a parallelogram. The next thing I'm going to do is I'm going to say that AB, forgive the typo here, it just didn't come through, or AB here is parallel to CD, and BC is parallel to DA. Right, that's, forgive the typo here, but that should be the parallel notation. Right, and that's just the definition of a parallelogram, right, that the opposite sides are parallel. The next thing we're going to see here is that angle 1 is equal to angle 4, angle 3 is equal to angle 2, and that's if the lines are parallel, then alternating interior angles are congruent. All right, we've learned that one before. It's got to be that AC is congruent to AC. That's just the reflective property of congruence, which we've used a bunch. Next, it must be then that triangle ABC is congruent to triangle CDA. All right, that's by the angle side angle. This angle side angle is congruent to this angle side angle. So then, because of that, side AB must be congruent to side CD, all right, and BC must be congruent to DA, and that's because corresponding parts of congruent triangles are congruent. So see how we used angle side angle to set up the two triangles congruent, and then showed that the corresponding parts of those congruent triangles are also congruent. All right, another one. Angles of a polygon that share a side are consecutive angles. So in the diagram, angles A and B are consecutive angles, right, because they're out on the same side, AB. But then also BC are consecutive angles, CD are consecutive angles, and DA are consecutive angles. So angles that share a common side are consecutive angles. So consecutive angles of a parallelogram. So if a quadrilateral is a parallelogram right here, so if ABCD is a parallelogram, then its consecutive angles are supplementary. So meaning if I take the measure of angle A and add it to the measure of angle B, that's 180 degrees. Measure of angle B plus the measure of angle C, that's another 180 degrees. And so on. CD sum to 180 degrees. And DA sum to 180 degrees also. Another one, all right, if a quadrilateral is a parallelogram, then its diagonals bisect each other. Right? Remember, when you bisect it, that means it cuts it in half, and the two sides of each bisector are congruent. So if ABCD is a parallelogram, and it got a little cut off here, and we bisect it with two bisectors like this, right, to form like this X in here, it's got to be that AE is congruent to CE right here, and then also on the other side, BE, and it get cut off, is congruent to ED. So the bisectors are congruent to each other. All right, let's use the consecutive angle theorem here. All right, so I've got this, desk lamp here, and what I'm saying here is that this PQRS is a parallelogram. So this side is parallel to this side, and this side is parallel to this side. My question is, if I know that angle S here is 64 degrees, what is the measure of angle P, this one here? Well, this means that we have this parallelogram that I said PQRS, and these two right here, S and P, are consecutive angles. So the measure of angle S plus the measure of angle P has to be 180 degrees. Well, I know the measure of angle S is 64 degrees. Subtract that over. The measure of angle P then has to be 116 degrees. All right, so the correct answer here is that C. All right, let's do this problem. So this is using algebra to find some lengths here. So I want to solve a system of linear equations to find the value of x and y here, right? And all we know is that KLMN is a parallelogram. And then I ask you, what are the lengths of KM, so the length of this total here, and the length of LN here, this total length here? Well, to find these lengths, we set up a system of two equations, and we're going to solve by substitution. Well, we know that KP is equal to MP, or y plus 10 is equal to 2x minus 8, and LP, x, is equal to NP, y plus 2. All right, so here were those two equations that I just said. So what you're going to do is you're going to take this top equation here. You're going to put it here, and you're going to notice this x that I have here, I'm going to substitute in for x. I know x is equal to y plus 2. Now watch what happens when I do. I get in a single linear equation in one variable, which means I can solve it. So distribute becomes 2y plus 4. Clean up the like terms here. 4 minus 8 is minus 4. Subtract the y over. I get 10 is equal to y minus 4. Add the 4 over, and I get y is equal to 14. Now, to find the value of x, choose either equation 1 or 2. And substitute 14 in for y. I'll choose equation 2 because it's a lot easier. So x is equal to y plus 2. Plug the 14 in, and x is equal to 16. Now remember here what I said is I wanted to find the lengths of km and ln. All right, so now let's find km and ln. So by looking at the parallelogram, we see that km is equal to 2 times kp, right? Because these two sides are the same, so just this side is the same on this side, so it's really 2 of them. And that ln is equal to 2 times lp by the same thought process. So km is equal to 2 kp. Well, kp is y plus 10. Well, we know y is 14. So it's 2 times 14 plus 10. Well, 2 times 24 gets me 48. And then it's the same thing on the other side. Well, lp is just equal to x. Well, I know x is 16, so 2 times 16 gets me 32. All right, so thus x is equal to 16 and y is equal to 14. So km is 48 units and ln is that 32 units. All right, one last theorem in this section. This is about multiple parallel lines and transversals. So if three or more parallel lines cut off congruent segments on one transversal, right, then they cut off congruent segments on every transversal. So if I have AB is parallel to CD, which is also parallel to EF, and this transversal is cut such that AC right here is congruent to CE here, then if I take any other transversal, it must be then that those segments cut by the transversal are also congruent. So this segment BD is congruent to this segment DF over here. All right, so let's do a problem. And sorry for the typo here. These are all supposed to be the parallel sides. So if line AE is parallel to BF, which is parallel to CG, which is parallel to DH, and I'm telling you here that segment AB is equal to BC is equal to CD, all these are equal to 2, all right? And that's a transversal that's cutting parallel lines and it's forming congruent segments. And EF, this segment right here is 2.25. What is the length of EH? So this total length from here to here. Well, we're given the lengths of segment EF, right, which I said was 2.25. Thus, to find TH, we need to find the lengths of the next segment, FG and GH right here, and then just add them together, right? Well, using that theorem that I just had here, if these segments are congruent, right, so these parallel lines are cut by transversal, these segments are congruent, it also means these segments must be congruent, or they're all equal to the same thing, right? So they're all equal to 2.25. Well, then how am I going to find the length of EH? Well, EH is just equal to 2.25 plus 2.25 plus 2.25, which gives me 6.75 is the length from here to here. Right, so that's 6.75 units.